So vehicle design is a big part of engineering, and drag is a big part of vehicle design. So an aerodynamic car much better on gas than a non-aerodynamic car, right? So if you are talking about car design, there are several several forces that the engine has to overcome, and one of those is drag, and we can also call that air resistance. Another one is gravity. So if you're going uphill. And finally, rolling resistance. And that would be from your bearings, flattened tires, etc. Really anywhere that friction is going to be caused. So for instance, flattened tires, you got a bigger frictional surface area there on the road, so that's going to cause higher rolling resistance. Okay, here's a graph that kind of compares some of these, rolling resistance and air resistance, and then gives you the total horsepower versus speed. Okay, so again, this is horsepower. So this is power versus speed, and you can see at low speeds there is very little drag. Almost all of your resistance to just going, if you're on a horizontal road, is going to be due to just the friction in the bearings and that kind of thing. But as you start to get up to past 45 miles per hour or so, you start getting on highway speeds, then the air resistance really becomes important. Okay, so and at about 55 miles per hour, it's about half and half. Okay, so, but what this is power. This is not just drag or rolling resistance force. It's power. And power is, if you remember, power is force times distance over time, right? So it's basically energy over time. So our drag power, if you take that distance over time part of it, you realize, oh, that is the speed. So our drag power is drag times velocity. And if you plug in for drag, that's 1/2 rho v squared CdA times velocity. So now you got a velocity cubed in there, and so you can see why this line increases so fast as you get up in the higher speeds. Rolling resistance power, on the other hand, it's going to be approximately FV proportional to V, approximately. So that's why it's linear on here. It's going to really depend, but notice though, remember that the drag is low at very low speeds, and then it goes up very quickly at higher speeds. So driving like a grandma is going to save you a lot of gas. Alright, so here's just some comparisons of some different cars. This data is a little bit on the old side, so if you wanted to look up newer cars, you could certainly Google it, but one of the better ones would be like the Honda Insight here. I'm not sure if they're still making those, but it was a hybrid. One of the worst ones, ooh, look at this Hummer. That's pretty bad. All the Hummers are pretty bad. Okay, so this though is CDA. So a lot of times it's not just reported as CD, because the area is also going to be important when calculating drag. So the CDA gives you a little bit easier calculation of getting to drag, and it's a better comparison. It's a much more direct comparison among all the cars than just coefficient of drag, okay, because of that area. So saving gas, like I said, drive like a grandma, and that goes for a lot of things. Drive slowly, you decrease drag. Alright. Properly inflate your tires. That decreases rolling resistance. Less braking. That means less energy loss to heat, because that's normally just friction. More coasting, that's going to cause less braking. Right? So if you come up towards a light, you see the lights turned red ahead of you, instead of accelerating until you get to the point where you need to brake, You can just take your foot off the gas, save a little gas if you're trying to save a little money. Slower starts are going to give you more efficient combustion. So if you slam the gas pedal down, that's no good. And higher gears are also more efficient. Alright, so if you drive like a grandma or like you're always in the snow, then you're probably going to save a lot of gas, and you can make a significant difference. It's kind of a fun experiment to try. I was able to make quite a difference by grandma driving. Of course, you can also make everybody mad that's behind you. Alright, so let's just go through an example. So here's a truck, and we're going to decide, is it worth it to put this little fairing on the top? Okay, and if you have a fairing there, or it's like a wind resistor here, you notice you're not going to have this 90-degree turn. Alright, so you're going to get, it's a little more aerodynamic, flow more like that. Okay, so let's do a comparison. So we're given a frontal area for this, 92 square feet. Same, both with and without the fairing. You wouldn't really be able to see that fairing if you're looking at it from the front. And we're given a rolling resistance per mile per hour. So let's go ahead and figure out the force. So the forces, like we said for vehicles, F total is going to be your drag force plus your rolling resistance, we'll call it FRR, plus possibly gravity. But this is on a flat, let me say flat road, so we can cross out gravity. Alright, so let's calculate rolling resistance because we have everything we need. I think if you just look at these units, you can figure out how to find rolling resistance. F rolling resistance is going to be this 11.2 pound-force per mile per hour times the mile per hour times 65 miles per hour. Comes out to be 728 pounds. Whew. Be hard to move that thing from a standstill. Alright, so what we need then is drag. So this goes in here, so all we need is drag. So we're going to need a drag, well, let's write the CD equation. CD equals drag over 1/2 rho v squared A. We got A. We're going to need V in something besides miles per hour. And then we can just calculate drag. And we also need a CD. Times CD times 1/2 rho v squared A. Alright. So what you want to do is look up in the book. This is a 3D shape. You look up in the 3D table and there's this exact picture here, with and without the fairing, and you'll see CD from table 7.3, CD without the fairing is 0.96, CD with 0.76. Alright, so see, these problems aren't so hard. So when flow gets complicated, we go to experiments and things actually get easier. So complicated means easier. In calculations, it also means less accurate though, unfortunately. Alright, so our drag then, again, it was 1/2 rho v squared A times CD. Okay, so if I plug in the 1/2 rho v squared A, that turns out to be 978. I'm not going to do the actual math. Pound force times CD. Okay, so that means then the drag without the fairing is 939 pounds, and the drag with 743 pounds. Okay, so our F total without the fairing, 1667 pounds. F total with 1471 pounds. Okay, so The question though is, well, what was the question? Find the horsepower requirements. Okay, so that's power, that's not just force. So now we have the force. In order to get power again, all we do is multiply by FV. Or power equals FV, right? Or FU. It's easier to remember FU sometimes. So power without the fairing comes out to be, just multiply by the 65 miles per hour converted to, I should have probably written up here, V equals, if you change from miles per hour to feet per second, it's 95.3 feet per second. Alright, so power without is going to end up being 159,000 foot-pound force per second. But we want horsepower, and the conversion is there's 550 foot-pounds per second in 1 horsepower. So the power without equals 290 horsepower. Doing the same calculation with this force, with the fairing, 255 horsepower. Alright, so that's our answer, but really, is that what we need to know? I mean, that doesn't look like that big of a difference. What we really would want to know, if this was a real problem, is economics, right? You want to know, okay, what's your miles per gallon? How much money are you going to save? So in order to convert these powers into miles per gallon and therefore costs, you can use this factor. Just looked up this typical factor, economics, typical factor online, and I found this EO, and I can't remember what it was called, but it said 13 for a semi-truck horsepower hours per gallon. And what that means is every 13 horsepower consumes 1 gallon per hour of fuel. Okay. So if we want to figure out our miles per gallon without the fairing and with the fairing, we can say this 13, and you can just kind of use units to figure out how to do this. Horsepower hour per gallon, okay, because we already got the per gallon on the bottom now, times 65 miles per hour times 1 over 290 horsepower. Okay, comes out to be 2.9 miles per gallon. Okay, if you put the fairing on, your miles per gallon with comes out to be 3.3 miles per gallon. Okay, terrible, really terrible, but still, I don't know, that doesn't look like that much difference. What we really need to do is figure out cost then. So let's say we got a long haul trucker, distance trucker, and they can go 100,000 miles a year approximately. Okay, and I said diesel was $3 a gallon. It's probably less than that at the moment, but it goes up and down, as you know. So the less expensive, the less difference this is going to make. But without the fairing then, 100,000 miles per year times 1 gallon for every 2.9 miles times $3 per gallon equals $103,000 per year. With the fairing, same calculation, you get $91,000 per year. Alright, so still you look at that, $91,000, but that saves $12,000 per year. That's significant. And that is per truck. So now if you got a fleet of trucks, say you got 1,000 trucks, then you're going to save a lot of money. If you had 1,000 trucks, that's $12 million per year for just that little bit of difference in miles per gallon. So ferrying would be worth it. I mean, your ferrying, how much is that going to cost? I don't think it's going to cost $12,000. So you're going to make up your money quickly. All right, and that's all I've got. Last video, you can finish the quiz. That'll be the last quiz, last video, and I will see you in class.